So thank you all for coming. Today we have Dr. Ross talking about Fourier analysis.
Okay, thank you for having me. Fourier analysis is something that does not actually appear in the EMU undergraduate math curriculum, which I think is a big oversight. I think it should be in there somewhere. It's possible to graduate from the EMU math department without having heard the words Fourier analysis, even though it's a fundamental application in a wide variety of things. So after this talk, I hope you go storming the math department offices saying, we want more Fourier analysis. Okay, I have here a data set that is the number of airplanes in the air over the US every 10 minutes for Tuesdays in spring. So what's the first thing I do anytime I have a data set? Graph the data set. Good. It's like some of you have taken my classes before. So here's a graph of it. Does this surprise you? So this is the number of airplanes in the air over the US every 10 minutes from midnight to midnight. Seem reasonable? Like, it seems to head a low around like 2 or 3 in the morning. Yeah, that seems reasonable. Okay, let's say I wanted to fit some kind of function to this that would give me basically the idea of what's going on. Like if I wanted to generate random values from this to test like an air traffic control system to see if it can handle the amount of demand that was going to be placed on it from all the airplanes. I want some kind of function that's fit to this that would give me the general idea. What kind of function would you use? A periodic kind of function? Now some people say, well, how about a cubic? So the cubic would come like down like this, up again, and then back down. And we all learned about cubics in Taylor's unit, right? Talk 2. So what do you think between a periodic function and a cubic? Sine or cosine would be periodic. What are the advantages and disadvantages of sine or cosine versus cubic?
You are literally in the period. I'm pretty sure that starts in the same place.
Okay, it kind of ends in the same place that it starts. So you think Tuesday would look pretty much the same?
Maybe not.
Well, I don't think it would be exactly the same. Mondays are different than Tuesdays. I think we all know that. But the idea that this thing basically repeats each day seems kind of plausible, right? The cubic would not have that property at all, whereas a sine wave would. So I want to fit a sine wave to this. Now this is a perfect sine wave, right? When you graph a sine wave, this is exactly what it looks like. Why not? In what ways does this fail to be a sine wave?
It's like weird dip at 2:30.
Okay, there's a dip at 2:30 in the afternoon or so. What else?
There's a really big stretch where it's sort of like a mountain, and then there's only a small valley on the other side.
Okay, so the time from here to here, well, I got to include this part too, right?
Correct.
So yeah, maybe it spends more time up high than it does down low. Okay, well, a sine wave starts at the origin and goes up, right? This thing does not start at the origin and goes down to start with. So it's not exactly a sine wave or a cosine wave. A sine wave goes between plus and minus 1. This thing does not go negative. I think we can all agree on that. And it goes between like 1,000 and 5,000. So I need to move the sine wave around, right? So what are the ways I can move a sine wave around? Tack a constant on? Okay, that's plausible. What kind of constant do I want to use? Okay, so the wave kind of went like that, right? So if I say, well, sine waves start in the middle and go up, then the sine wave, if I did that, that would be a sine wave. So I can talk about, well, it starts at some time other than 0. You can call that the horizontal shift. What else does it do? It doesn't start at the origin, it starts up here. I could talk about the vertical shift. What else does it do?
Scale it.
Yeah, it doesn't go between 0 and 1. We were talking about numbers in the thousands. So I could talk about that distance, that's the amplitude. And how often does it repeat? Every 2 pi radians? How often does it repeat?
24 hours.
Every 24 hours. So that's the wave. So wavelength is 1 over frequency, right? So I gotta think about all these things. So I don't want to just do f of t equals sine t. That fails to capture a lot of what's going on. I need to do f of t equals, well, usually we'd add the vertical shift plus the amplitude and sine of frequency times t minus the horizontal. That's all your good trig stuff. Summarize very quick. So I want to choose the vertical shift, the amplitude, the frequency, and the horizontal shift to make a sine wave fit my data pretty well. So if I put that graph back up, if we all eyeballed it, like what's the vertical shift, you say? We'd all get exactly the same number, right? And for the amplitude, we'd all get exactly the same number. Well, maybe there's a more objective way to do it. So let's start by guessing some numbers. Guessing is always a good first step, but you don't want to stop there. So let's say, what's my vertical shift, my amplitude, my frequency, and my horizontal shift. I'm going to put some numbers there. Let's just eyeball, what's the vertical shift there? That was like the center line.
2,800.
3,000. I think 3,000 is close enough to start with. 3,000. How about the horizontal shift? It was like, so here's 9:30 a.m., maybe 8 a.m. At this point is kind of like the origin, so an 8-hour horizontal shift. How about the amplitude? That's from the center line to the peak. About 2,000? So 2,000 amplitude, horizontal shift of 8 hours. And the frequency, okay, if we all eyeball the frequency, will we get the same number? We're pretty sure it's 24 hours, right? We don't think like it's 25 hours maybe. Because if it was 25 hours, then if that happened over and over again, it would gradually get out of phase with the day-night cycle. So we're pretty sure it's 24 hours. So for that, I can type like 2 pi divided by 24. Okay, so I'm going to have a column of predictions here. I'm going to say vertical shift. Actually, I can name each of these cells to make my formulas look nicer. And I can say vertical shift plus, there we go, plus amplitude times sine of frequency times my time value. Time value minus my horizontal. So that's just the formula I wrote up on the paper here. Except I don't know that's the time. But one thing I have to think of here, my time looks like it's a number like 12 or 1, but this is actually showing what it is. It's a number between 0 and 1. Excel is keeping track of time in days. So 0 to 1 is 1 full day. So 0.5 is noon, and 1 is the next midnight. So I have to know how it's keeping track of time. So in fact, my frequency here, it is going from 0 to 24 hours, but it's really going from 0 to 1 day. So I don't actually want the 24 in there, I just want the 5. So those are the 2 ones. So I'll do all that, and then I'll make a new graph. Okay, how did I do on my predictions? Well, it's not totally bad. What needs adjusting? Did I get the center line right? The vertical shift? Did I get the amplitude right? Did I get the frequency right? 1 cycle each day? Okay, what did I get wrong? The horizontal shift. In fact, it's not just that I got the minus or plus wrong on that. It's that I wrote it in hours, 8 hours, but I forgot the time minutes or days. So what's 8 hours as a fraction of a day? It's 8 over 24, right? Got this machine, let it do the math. Okay, is that looking better? Okay, so the question is, how am I going to tell Excel to adjust those numbers to give me the best possible fit? One way to do that is to say, well, how far off is my prediction from the actual data? So I'll just take the vertical distance from my actual data to the prediction. And that's called the residuals. Can you ignore that? So residual is actual minus predicted. So that's just that number minus that number. Once I have the predictions, I had to put a lot of trigonometric thought into the predictions. But once I have them, residuals are easy to calculate. What was my guess? What was the actual? How far off am I? Okay, so that gives me a bunch of numbers. And do I want these to be big or small or what?
0.
Ideally, 0. Do I think I can achieve all of them being 0? Not unless my data was an actual sign. So I want them to be small, like as negative as possible. Negative is small. Close to 0 would be good, right? Because if they were all negative, like I can do that by, if I make this vertical shift like 10,000. Look, all my residuals are really negative, but that's not a good prediction. So I want them to be near 0, not near negative infinity. So I'll undo that. So I need to say, I want their sum to be near 0. And it turns out that's not a bad idea, but I can do better by squaring each one first to make sure I don't get any negatives. So Excel actually has a nice way to do that. Get rid of this. We do it so often, Excel has a fast way to do it. Instead of just saying sum, you say sum s cubed. That squares each one and then adds them up. Okay, that is a big number. What are the units of that number? Is it just airplanes? No, it's airplanes squared. So we don't want to deal with it. mean, we can kind of live with it, but just keep in mind it doesn't really mean anything that we're used to. So I want to minimize that number by adjusting these things. Okay? Do I actually want Excel to adjust all of these things?
No.
Why not?
Well, the frequency we know to be good.
Yeah, we're pretty sure on that frequency. I like to have Excel only adjust things that are kind of in a block, so I'm going to move this around. And uncolor that one. Okay, so I want Excel to adjust those things to get that as small as possible. So there's actually a tool in Excel to do that. It's an add-in, but I can show you later how to add it in. It says set objective. What's my objective in life? Well, probably something about like treating other people the way I want to be treated. But for now, what do I want to do?
You want to set the airplane square to 0?
I want to get that. I'd like to set it to 0. Do I think I can actually achieve that? No, maybe just try to get it as small as possible. What variable cells is Excel allowed to play with here?
B1 through B2.
Those ones, right? The variables are in verde. The objective is in orange. Do I have any constraints? Anything I have to keep true here?
Yeah. Frequency.
Okay, I could tell it don't adjust the frequency, but in fact I didn't tell it where the frequency is hiding. So I think I'm okay there. Let's see, I don't need non-negativity. Do you think this is a linear problem or a non-linear problem? I had a sine wave in there, and then I was squaring stuff, so it's probably non-linear. So this non-linear thing is probably what I'm going to solve. It says it found a solution, so it must be right, because it's, it's a computer, and it's Microsoft. Well, we can go take a look. Does that look a little better than what I started with? Yeah, I think so. I think this was bigger, not that I remember exactly what it was. It's probably bigger. So here's the question. Are there any patterns left? Did I find all of the patterns in this data? Well, I've got my data, I've got my prediction. What's left over? The residuals. In fact, that's a big column of numbers that I didn't graph yet. Maybe I should graph it. So I'm going to graph all of this. So now here's my predictions, my actual, and here's my residuals. Are there any patterns left in the residuals?
Yes.
What kind of pattern?
What's that?
There's a sine wave. Didn't I just take out a sine wave? There should be no sine wave left. Well, what's different about this sine wave versus the sine wave I fitted already? It's much shorter. Its center line is basically 0. Anything else?
Bigger, more frequent.
More frequent. That's the big thing here. My original wave did a wave once a day. My residuals go high, low, high, high, low, high. They're waving twice a day. Huh. Maybe I should include a twice a day wave in my original fit. So let's give that a try. We'll keep our original one here just in case we mess up. Okay, so then I need another block of values. I call this like, no, set these to 0 to begin with. And then my predictions, I'm already doing that. And then I'll do it again, but with the new vertical shift and the new amplitude times the sine of the new frequency times minus the new horizontal shift. Okay, so it's basically the same thing as before, but using these other values. Now I have to do some weird Excel stuff here because I didn't name those cells. I need to lock these references. You can ask me later what's up with that. And that's still not. Okay, nothing changed. Those were the same numbers I had. That's because I set all this stuff to 0. What's the new frequency? Half the old one? The new wavelength is half the old one. The new frequency is twice as fast as the old one. Now, I can actually go back down here and look. What's my center line for the residuals? Basically 0. Okay. What's my frequency? I did that. What's my amplitude? From the center line to here, 1,000 maybe. Okay. And how about my horizontal shift? It still seems to be about 1/3 of a day. Let's go up an amplitude of 1,000, basically 1/3 of a day. So now let's go see, there's my new prediction. It's kind of hard to tell if that's good or not, but we can tell it's self-optimizing. So let's give that a try. So I still want to minimize that sum of squared residuals. Now my decision variables are those. Still nonlinear. And let's see. Do you think that's better than my original? Okay, are there any patterns left in the residuals? What kind of pattern is left in the residuals? It looks like a sine wave. How many times a day does it wave? So it's kind of 1, 2, 3. So to summarize, I fit a once-a-day wave, I looked at the residuals, I saw a twice-a-day wave. I fit a twice-a-day wave and a once-a-day wave, I look at the residuals, I see a 3-times-a-day wave. How long can this go on? Infinitely, maybe? Actually not. Because once I ended up with as many waves as I have data points, I can fit each one exactly. But I don't need to worry about that right now. No, we don't have that much time. Okay, so this is the idea of Fourier series. Take something that you think is periodic, maybe sort of sine wave-like, and fit waves to it, and see what's left over. Oh, gee, there's a faster wave going on. Okay, we'll fit that too. Oh, gee, there's an even faster wave going on. So we just keep doing that, right? So let's see. One thing we can do here, let's take a look at the at these parameters. First of all, what is that number? Basically 0. Does it really pay to have 2 vertical shifts, like shift it here and then shift it again? Not really. So I can pretty much ignore that one. So I'm going to write down these numbers, but in a particular way. My first vertical shift is 3170. So I'm going to put that here at a frequency of 0. If a wave has a frequency of 0, how often does it wave? Not at all, right? It's like a horizontal line. It's like a vertical shift. Okay, so that was my first frequency. Then at a once-a-day wave, I had a frequency, an amplitude of 1958. That's about there. And then at twice a day, I had an amplitude of about 600. 16. So if I wanted to, I could go fit a faster wave. Those residuals were even smaller, though, so its amplitude would be even smaller, right? We didn't do this, but we think its amplitude would be smaller still. So that's showing us how much amplitude is on each wave. The vertical shift, the once a day, the twice a day, etc. So this graph, or these values, is called the spectrum. And I'm using that term very loosely. For people who know what I'm talking about, yes, I know it's not quite the same thing, but it's close enough. So that's the spectrum. Kind of like red light has a lot of power in the red frequencies and not much in the green and blue frequencies, right? So if you made a little graph here of light frequency, red light has a lot of power in the red frequencies, but not the green and blue ones. Blue light has a lot of power over here in blue frequencies, but not in the red and green ones. So just like you talked about the spectrum of light, or a rainbow, here we're talking about the spectrum of some other periodic signal. Okay, any questions so far? Yeah.
When we're taking the frequency into account, are we adding the frequency or multiplying?
So I said I had a once a day wave, right?
Yep.
And then a twice a day wave, and then a 3 times a day wave.
I was talking about in Excel, because you multiplied it by 2, and I wasn't sure if by 3 you would just multiply it by 3 initially,
Okay.
or if you would take that and then multiply it again.
So if I was doing this more, here I would go equals 3 times my original frequency.
Yep. Okay.
So I wouldn't do 3 times this number, which was already 2 times that. I would just, does that answer the question?
Yes.
All right. Now, so where else do we see this kind of behavior? Well, actually, we hear it before we see it. So here we've got one of my favorite apps. Let's see. Where it goes. It was on here. All right, so this is an oscilloscope, or it's acting like an oscilloscope. An oscilloscope graphs oscillations, oscilloscope, or makes them visible. Right now it's listening to the microphone, and the air waves from my voice, the pressure waves, are pushing on the microphone back and forth, and that's what it's graphing, right? I know not everyone grew up with an oscilloscope at home, but that's what this is doing. So, does this look like a sine wave to you? It doesn't look like a sine wave to me. Can we make it look like a sine wave? It's not bad, right? It's not like I know anyone who spent his time practicing whistling exact sine waves. Okay, and can I make it look like a sine wave that goes faster or slower? No. So the waves got closer together, right? Well, that's a good graph. We like that graph. Wouldn't it be nice if there was a graph like this that showed you how much amplitude was at the different frequencies? Well, sure enough, there's a button here called spectrum, and that shows for each frequency along the axis here how much power is at that frequency. So if I go, you can see it's seeing just power at that one frequency as it moves up. So that's a spectrum of what the microphone is hearing right now. Any questions on that? Okay, well, the problem with this graph is that it goes away so fast. Right? Maybe it'd be nice if we had a history of what had been there. So now we'll try a different app. Spectrum view. Funny how it's called spectrum view. the way, these apps are both free or 99 cents or something. Lots of benefit. Okay, so now it's still listening to the microphone, and it's showing me time along this axis. It's showing me frequency along this axis. And then intensity, which was the height of the spectrum before, is now color. So reds are most intense. So you can't really see very much here, but if I try to get a single sine wave again, you can see it pretty clear. In fact, you can also see that there was a little bit of power at twice that, so I wasn't listening to pure sine. So I've actually seen this in bird watching books. I saw a bird watching book that had spectra, time spectra of a bird call. So if you saw a graph like this, it would have that. It was expanded out a bit, and that is the sound of, anyone know? Cardinal. Or a cardinal. I was trying for a cardinal. So you could see the spectrum and imagine what the frequency was doing, and think, okay, what will that sound like in the wild? So yeah, there's whistling, there's bird calls. What about singing? Now I won't attempt to sing, but I'll just make some sort of note that will pretend to singing, right? What if I go la? See, there's not just one sine wave, there's a lot of them. And if I say E, can you tell the difference between la and E there? It's how much power is in these frequencies versus those, and there's a little band up here. This is also the difference between like a trumpet and a clarinet and a tuba and all kinds of things. They have different amounts of power in different places, right? So how about this one? So there's a lot of those harmonics in there. Everything other than the first wave is called the harmonics. And this is a?
Harmonica.
Okay, ready to go on? If you want to do demos like this in class, they're lots of fun, except you can't have everyone singing to their own smartphone at the same time, because then all the spectra gets muddled together. All right, let's have a brief technical interlude. When I was doing this stuff, sine of frequency times t minus the horizontal shift, that's a nonlinear function, right? It's a nonlinear function of horizontal shift. I sure do like linear functions, though. So I can linearize the horizontal shift using a trig-identity. So basically what I have is sine of some frequency times t plus some phase shift. And there's a trig identity that says this is equal to a times sine of frequency times t plus b times cosine of frequency times t. And a and b here are a function of the phase shift. We don't need to worry about that at this point. But what this is saying is, if the phase shift is 0, it's just a sine. If the phase shift is 90 degrees, it's just a cosine. If the phase shift is something between 0 and 90 degrees, it's a mix of a sine and a cosine, all at the same frequency. So instead of using a nonlinear parameter here, I can use two linear parameters. So that makes all the calculations a lot easier. So now let's do. Okay, there's an app here that someone invented at Halstead.com. Here it is. Okay, so can you see the red curve here? That's a sine wave. if I ask for its spectrum, here it's showing me the spectrum in terms of coefficients on the sine and coefficients on the cosine. And sure enough, there's a lot of power at one frequency and no power anywhere else, because it's a pure sine wave. So I can even listen to this. So this isn't too loud. Oh, sorry. Okay, so that's what a sine wave sounds like. Here's what a cosine wave sounds like. Can you tell the difference?
Where it started.
Where it started, and you heard a little click when it shifted. But the difference between sine and cosine to your ear depends on how close you are to the speaker. You don't want things to sound different if you're just a few centimeters closer or farther, right? So that's in some sense why our ears don't hear frequency, don't hear phase shifts very well. So this is a sine wave. I'll turn it even more down. This is not a sine wave. I think you'll agree. This is called a square wave. And look at all the spectrum it has. It has fundamental power. The next harmonic is 0. One after that has some power to it. After that, there's another 0, and then another one, and then another 0. And the weird thing is, if I add up all those sine waves, I get something like a square wave. Can you hear how the square wave is different than the sine? So the difference is you're hearing all of these higher frequencies. It's a little more annoying than a sine wave, you could say. It's got a little edge to it. But guess what? I can filter out those high frequencies. Can you hear that difference? And I can add them back in. So you can use Fourier analysis to filter out high-frequency stuff. If you filter out high-frequency stuff and then amplify the rest, what have you done? Pumped up the bass. Good. You know how when it was really loud, it didn't sound as nice as when I turned it down, right? Even the sine wave sounded terrible when it was really loud. What was going on there? The speaker was trying to move like this. But it's only allowed to move in this range. So what happens if it tries to move over here when it can only move up here? It flattens out, it hits this and stops, and then tries to go and hit the other end, but it stops. So over-amplifying something ends up clipping it, and you end up with something more like a square wave, and it sounds worse than a plain sine wave. Sawtooth has even more high-frequency stuff than a square wave. Back to square wave, am I getting a nice approximation of my square wave from all my sines? Like, okay, that's better. That's even better. Right? It's doing good flat things here. Is it just getting more and more flat? Well, it's hard to see, but let's go take a look at this animation. Maybe that's easier to see. It's getting flat in the middle, but it's still got this overshoot that's not going away. It's moving to the edges, but it's not going away. That's called Gibbs phenomenon. And it's kind of like if you tried to move your arm from here to here instantaneously, does your arm stop dead where it should stop? Or does it get there and kind of oscillate a bit? And then trying to move back, it oscillates a bit. So there's even a mechanical analogy to it. All right, so I think we're done with Fourier, with that app. Now it turns out people have been thinking about this for a long time. We're going to go old school for a sec here. People arranged machines where you could move a stylus along a data plot curve that you plotted, and it would record the appropriate amplitudes on some drums. And then you could then you could crank it forward and it would keep predicting based on the sine waves that you had recorded in your data. So people use this to analyze tides. You know, here in Michigan we don't worry about tides much in the Great Lakes. But if you grew up on the coasts, tides are more of a thing. And tides happen twice a day, but they also depend on where the moon is and how far the Earth is from the sun and all kinds of other stuff. And so there's all kinds of sine waves in there. And people actually built machines to help analyze them. All right. Which maybe I should point out the math department does not currently have any of those machines.
Someone could build one.
Someone. All right. So have I covered everything in my abstract? What did my abstract promise you that you have not yet seen?
A biomechanical device.
Biomechanical device. Okay, well, we aren't going to see that today, I hope. But we'll talk about it. I talked about kittens, right? What is the foundational aspect of our society? What is it we as people do? We take pictures of kittens and send them to other people over the internet, right? So here's a picture of a cat. And how do we compress things? We use JPEG technology. Oh, one thing I forgot to mention. When we were doing this audio app, your ear often can't hear these high frequencies. And so to save room in making an MPEG file, an MP3 file, it just leaves out some of these higher frequencies, or at least stores them in reduced resolution. So that's how it compresses sound, by leaving out stuff you probably couldn't hear anyway. And it has a very sophisticated model to do that. It's not just like, well, most people can't hear above this frequency. It's like, well, there was just a loud sound in this range, and so you probably can't hear anything in this other range for the next 0.02 seconds. So it's called a psychoacoustic model. And they use that to decide what to throw out. So that's how sound gets compressed. How do pictures get compressed? You break each picture into 8 by 8 pixel blocks, and then express those not as a sum of a sine wave, but as a sum of a sine wave going this way and a sine wave going that way, because it's two-dimensional. In fact, for technical reasons, people use cosine waves instead of sine waves. So that's hence the title, Kittens cosines. So instead of just once a day, twice a day, 3 times a day, 4 times a day, here we have one wave. It's actually half a wave, 1.5, 2.5, 3.5, 4.5 in the x direction. The same thing in the y direction, and then all kinds of mixes of them. And so we express each 8 by 8 pixel block as a weighted sum of all these 64 patterns. But you know what? Your eye isn't very good at seeing detail this fine. So we just don't bother to store those, or store them in reduced resolution. And that's how you achieve image compression. And then a video is like a JPEG, but over and over again with some extra tricks about moving around. So sometimes if you're watching compressed video and it was compressed at a really high compression, or there's interesting things going on like fireworks on the night sky is a lot of really fine detail, you can actually see the 8 by 8 pixel blocks popping up. Okay, so now we've talked about kittens. Anything else we need to talk about? What's that?
Parts.
Parts?
So that's biomechanical.
Oh, it is. Does it use Fourier transforms? Not as far as I know. Let me just check that. Okay. So we said some attendees will leave with a biomechanical device that implements this method and will keep working 24/7 for decades. Does anyone know what that is? Not your brain. Oh, by the way, just for the pure math people here, Fourier transforms can also be used to multiply numbers. If you have two numbers each 1,000 digits, sure you can do the usual multiplication algorithm, but it's actually faster to take the Fourier transform of both of them, add those together, and then un-Fourier transform it. Fourier transforms can be faster than multiplying for large numbers. Okay, raise your hand if you have a cochlea. A cochlea? A cochlea is the thing in your ear. Let's find a picture of it. this wound up thing here. And what that is, so pressure waves come in and hit your eardrum and bounce the cochlea around. The cochlea is kind of like a long stick, but curled up. And as a pressure wave bounces it around, part of it resonates. And if it's a high frequency note,